Good afternoon, everybody. I hope you can all help me give Arthur Pastel a warm welcome. He's here to tell us today about demystifying AsyncIO.
Thank you. Oh. Hey everyone, thank you for coming. Hopefully you will learn more about AsyncIO and understand how the event loop works after this talk. So maybe a little bit about myself first. So I'm a software engineer. I'm from France, probably you guessed with my accent. And I've been contributing to open source a bit before a few years ago, building an open source object document mapper, like a kind of ORM, but for MongoDB. And so this is really what got me started with building AsyncIO applications. And later as well, I've been a CPython typo contributor, fixing a really tiny thing. And now I'm working on performance and trying to improve it with code speed. But we'll come back to performance later, and it matters a lot with AsyncIO. So maybe we're going to start with a little sport and little exercise. Can you raise your arm if you ever heard of AsyncIO? So probably, since this is the title of the talk, maybe the event loop. Did you heard about it as well? Futures. Okay. Callbacks, maybe. Okay, still. Coroutines as well. Okay. And tasks. Okay. And selectors, maybe. Okay. So at least there is something we can get out of this talk. So the basic structure of AsyncIO and the basic principle is that we can suspend the execution of a program. So probably if you're familiar a bit with AsyncIO, you understand what this does, this piece of code. It will first execute the print statement, and then it will await for a future. So we'll dive into the details of what is a future later. And then it will resume the execution of the coroutine and actually print world. So this will give something like this, and then that. And then the only tricky thing is that we use AsyncIO.run to actually execute this program. So this example was nice, but not doing actually anything interesting with AsyncIO. So for example, let's say I want to fetch some Pokemons from the Poke API. So it's an API where you can fetch some Pokemons, and it's really useful for building toy examples like this. Without AsyncIO, basically I will use requests and fetch my Pokemons in a synchronous way, so with the encounter a Pokemon function. And then I will just have a loop that will loop through like 5 iterations in this example and fetch one Pokemon by one Pokemon. So what this gives is an execution kind of graph like this. So first we'll start by sending the request, then we will wait on the I/O, waiting for the server to send us an actual Pokemon, and then we'll receive the object. And we'll repeat that 5 times to actually get our 5 Pokemon. But this is not really a very useful use of our time, and actually the GIL time, because while we're waiting on the I/Os, we could actually do something else, because the GIL will mostly lock and like deny multiple threads to run in parallel. But since it's not locked while we are waiting on the I/O, we could do something else. And that's kind of the point of AsyncIO. It's while we are waiting on the I/O, we can do something else. And for example, we could just send all of our requests in a parallel way, but note that actually the red parts are CPU bound parts, and it means that they cannot run in parallel, but the green parts, where we actually wait on the I/O, are executed in parallel, and they can be executed in that way. And so the whole point of AsyncIO is to be able to do that in a simple way, because we could as well do exactly the same with threading, but the API is not as nice, and AsyncIO really gives a handy way to run parallel tasks. And so, for example, if we implemented that in an AsyncIO manner, it would look like this. So we would use, for example, here HTTPX instead of just request, which will allow basically the program to give back the handle to the event loop and run other code while it's waiting for the result of the async program, of the async request. And so you can note that on the bottom there is AsyncIO.run, and actually it's a bit of a simplification because it's hiding a lot of AsyncIO mechanics behind this. And this is actually where the event loop comes from. So when you do that, it will fetch the default event loop or create a new one, and it will create a task to actually run our code and then run the event loop until our code completes. So to understand how everything works, we're gonna create our own event loop. And the ultimate goal is to run this FastAPI application. So it's pretty simple, but just sending a hello world message. And the goal is that our event loop will be able to serve those requests. So the beginning and the most basic thing we can do with an event loop is to schedule callback. So we'll see like the point of scheduling callbacks just later on. But the most basic thing you could do is just schedule execution of callbacks. So a callback is basically a function that you want the event loop to call, but later on, not right now. It's just scheduled to be executed. And once your event loop will be running, it will execute those functions. And so here in this example, for example, we schedule 2 callbacks, and then we run our event loop. And the main idea behind this is that in our event loop, we have a queue of those callbacks. And every time you call the call soon method, it will add a new element in that queue. And once actually we'll run the event loop, those callbacks will be popped and they will be executed in an asynchronous manner. So if we go like in the actual implementation, our event loop will start with basically just creating an object. So this object will contain a deck. And so this deck is kind of like a list, but just allowing us to push and pop on the both sides in a constant time. So this is why we use a deck. Actually, there is a lot of potential implementation we can do here instead of using a deck to insert the task in the queue, but we'll come back to that later. And so when we use call soon, we are creating a handle. So a handle is basically a callback plus the arguments we want to send to that callback when we execute it. And we put that in our ready handles queue. And when we actually execute the code, so when we use the run forever method and the run once method, then we'll pop the callbacks and execute everything. So this is great, but it's not super interesting because we can just schedule callbacks and just with this method, it's not super useful. So another basic implementation and basic functionality of an event loop should be to schedule the execution of callbacks later on. So for example, here we can schedule the execution of the world callback, but 5 seconds later. And this implementation is actually quite close to the first one. So the idea is that we have another queue, but that is sorted, and we sort by the time when the callback should be executed. And so instead of putting the handles directly in the ready handles queue, we put them in the scheduling queue. And once our event loop is running, we'll then pop this queue and put the callback in the ready handle when they should be executed. So if we dive in the code, the main idea is that we'll insert in a sorted manner. So to do that, we use bisect.insert, which helps us to insert the element, the new callback, exactly at the proper place. And then we set it as scheduled, and we return the handle. Once then, we execute our event loop, and we execute each ticks of the event loop. We'll pop those callbacks when they are ready and put them in the ready queue, as shown in the previous schema. And so we can actually build another abstraction from that, which is the call later. So instead of just taking a time with call at, we can just call at with a delay and schedule execution of callbacks later on. So this is just like scheduling callbacks. But on top of that, like the main point of AsyncIO is to use results and to handle actually non-completed operations. And this is done with futures, so you probably heard of that. So the main idea behind the future is that it can be either pending or it can be a result. So for example, when the operation is in progress, the callback will be pending. And when you set a result, it will be finished. So this is a really like basic functionality of a future. But we can bring more advanced functionality, like scheduling, adding callbacks to the future. So when the future completes, we will execute some piece of code. So for example, here we create a future first, and then we add a on future done callback, which means when this future will be completed, it will just print future is done and along with the result. And then we can schedule the execution of this future. So we'll just schedule that in 1 second, the future will take the value 42, for example. And from there, we just execute the function, and this will print this when the future is completed. And so you probably noticed the loop run until complete function. And this is actually a variant of the first loop run forever, but here, instead of just running forever, we run until the future is not done, which is handy because often we don't really want to run the event loop forever, except for HTTP servers or specific use case. So now that we know about futures and as well about setting callbacks, we can work on various AsyncIO helpers. So for example, if you want to implement the sleep feature, actually we won't use just time.sleep, which would block the execution of the code and not really give back the handle to the event loop. What we do is we create a future, and we schedule this future to be completed X second after the call. And then we return this future. And this means when I call this function, I will get a future, and this object, kind of magic object, will be completed X second after I get it. And this is how we sleep, because during that period of time, the event loop can do anything else, and you can schedule anything else, but just the callback will be executed at the proper timing and resume the execution. As well, we can work on multiple futures using the gather method. So I showed it in the first example. And the main point of this method is to aggregate multiple futures into one single future. And so here the strategy is pretty simple. The idea is that we keep a count of completed futures. And every time one of our future is done, we'll increase this count of completed futures. And if at some point we encountered enough futures, it means that all the futures have been completed, and we can actually return the global future that will be set and not pending anymore. And this is a very partial implementation. Like if you go to AsyncIO and the standard library, you'll find that it's actually way more complicated than that, because here we're not handling exceptions and many other parameters, but this is the basic idea of like how we can group multiple futures into one. So until now, we talk about like scheduling futures, but this is not just async, it's AsyncIO. And so about the IO part, this is where it really like gets its power. So the main concept behind this is that instead of just waiting on futures that we set manually, we could also wait on read or write objects that would actually write either to a file or read from a file, or also like communicate over the network, either sending data or receiving data. And so this will be represented by a file descriptor. And the idea is that our event loop will map each file descriptor, so it might be a socket where you're sending a request to, with its callback. And so for example, when the file descriptor of your database request will be ready, we'll execute your callback, and we'll actually retrieve the object and give you the object to process it. And this is done in the AsyncIO API and like in the CPython definition of the event loop by adding and removing readers and writers. And so for each reader and each writer, we bind a file descriptor to a callback and its arguments. And this is the core of AsyncIO and the way and the reason why you can handle multiple operations in parallel. So the piece of software that really allows to define which callback we should call and when is the selector. And the idea behind the selector is that it will be able to wait on all those file objects, either they are in write mode or read mode. And once one of those objects is ready, then it will be able to match the appropriate callback and schedule it in the event loop. And so actually the selector's implementation, I won't dive into it, but it relies on a system call that allows to wait on multiple file objects. So this is a select system call. And so it will wait until one of the file descriptors contained into those lists. So there is a read list, write list, and then X list, which will contain like errors or wait for errors or exceptional conditions. And when one of those objects will be ready to write or to read, then it will return this object and will know in our event loop that actually we need to schedule the callback for execution and to continue the execution of the global code. And there is as well a timeout, which means if you set a timeout of 1 second, after 1 second, if none of those objects are actually ready to execute, then return the thing and the execution of the event loop will continue and a new tick will start. So we talked about the implementation of the selector part, but now there is a big part of AsyncIO, which is the syntax and how we actually define process and the way they should execute. In the beginning, it was defined using generators because they are really convenient, and it's a convenient way to have a function that can be started and then resumed at another point, because every time your generator will yield, you can actually do something else. And then when you have your data ready, you can come back to your function and resume the execution. So under the hood, now with the async await syntax, it uses kind of the same thing, but the syntax is way more convenient and easy to read. And as well, it brings some extra functionalities like async context manager that will bring async with, and as well async iterators that will bring async for functions and possibilities. And for example, async for is super useful if you're like fetching database records, because you don't want to fetch all of them at once in one huge request, but you want just to fetch the ones that are ready as progressively, which is more efficient because it allows you to fetch in a lazy manner. So if we go back to the previous explanation and kind of deep dive into AsyncIO.run, as well there was something named create task. And so if we dive into the task is actually what is the link between the coroutine and a future. So a coroutine by itself cannot be run, but the idea of the task is that it will take your coroutine and its argument and it will execute them and schedule them properly in the event loop. So for example, if we take this example, so fetch Pokemon is our coroutine, and then we create a task. And when this task is scheduled, the execution will start by scheduling the first step in our event loop. So when for the first tick, we'll execute the validate name method, which is a synchronous method. Then the await client.get to find actually our Pokemon will be triggered, and this is an async function, so it will open a connection and add the writer to the selector, because first we need to write and send our request. Once this is done, we'll just wait for the write to be possible, because maybe for some reason the connection is not possible and it's used by other devices. Then when we receive the data, we'll add a reader that will wait for the result of the query to come back, and we'll wait for the read. And once the read arrives, we'll schedule the rest of the execution of the event of this coroutine. And so this is the main goal of the task, being able to combine a future with a coroutine. So if we sum up everything, we handled the big AsyncIO piece and its syntax, as well the event loop, how to define it, futures, callbacks, and coroutines, and also tasks and their relationship with the selector. And after some network implementation, it can run a FastAPI server. So I won't show the deep dive into creating the server and everything, but it's available on the repository and you can find it. I'll show the link later with the slide. And yeah, it can run the server and actually print an hello world message. And so you see all my crappy logs done with sprints, and it's possible. So yes. And now we can think about performance, because we built a kind of crappy event loop. But how could it become more powerful? How does it relate to the default CPython implementation? There's still a lot of code in the event loop. So when you do an await instruction, it's not just some magic. There is a lot of code that is executed, scheduling, executing your coroutine, maybe resuming the execution of the generator. And there is a lot of code that actually execute. And so how is our event loop comparing with the default one. Actually, it's super slow. So it's 97% slower than the default implementation, mostly because a lot of optimization have been done. And our implementation doesn't even handle exceptions and a lot of bad behavior. So here I created some benchmarks for multiple basic instructions that we've seen before. Like, for example, waiting just for one tick, or scheduling a callback and inserting actually the callback in the queue at the proper timing. So depending on the implementation you choose, this will be different. And in ours, it was not really like in a constant time that you could schedule a callback to be executed. So this is one of the big reasons. You probably heard of UV loop as well. So this is a drop-in replacement of the default event loop. And it's built using Python and libuv. So libuv is the core building block of Node.js, and it's what powers its event loop. And so Node.js probably strongly inspired Python to come to a async-await implementation. And so this kind of brings back the whole world because libuv is used in a lot of different event loop implementations. And this event loop claims to be between 2 and 4 times faster. And so I used the same benchmark I had to compare and actually verify. And it's completely true. It's very way faster than the default event loop of Python. So it has more constraints because it's not pure Python and you need to compile it and it's more complicated to set up. But down the road, it's faster, even for simple operations like just scheduling a callback, either to be called directly or later on. And we can see that actually it performs better in all kind of different manner. So I built this report using CodeSpeed. So this is a project I'm working on since 1 year now. And the idea is to measure performance in a continuous way and in a consistent way. Because, for example, here we can see that even small instruction and just the overhead of an event loop can actually be dramatic. And so just running asynchronous code from changing your event loop, you can change the performance of your bigger application a lot. And so the main idea is to measure performance consistently and to run on CI without noise. So all those results that you saw were computed on GitHub runners, and this is super stable. So I don't have to really worry about someone else running other code next to me and adding some noise into the result. And I'm pretty sure that every time I will have some consistent results. And as well, it's fully integrated with GitHub and brings the performance report directly into your GitHub pull request, so you can as well continuously think about performance when it really matters and you're degrading the performance of your application. And on top of that, we bring deterministic and differential profiling to help really pinpoint where the performance issues are coming from. And it's free for open source, so if you have an open source project and want to measure its performance continuously to make sure it's getting only better, don't hesitate to reach out, and I'll be happy to help you. And so that's it. Thank you. And and if you have any question, I'd be happy to answer them.
Yes, sir. If there are any questions, we have a microphone here at the front for anybody.
I don't have much to ask. I just wanted to say that you did a very good presentation. But one thing I'll have to say is I wonder what is the last time you used AsyncIO or everything you talked about in a project generally, or what specifically did you use with that, and how you got what you wanted with that?
You mean the last time I used it?
Well, something more specific that you did with it recently.
I worked on an adapter for MongoDB, for example, really trying to make AsyncIO simple to use with Pydantic. And so, I mean, this is not super recent, but I've kept maintaining it. And so, yeah, this is the biggest work I do with AsyncIO, and as close as I can get, building asynchronous generators and context managers, bringing transaction directly with the AsyncIO context, for example.
Right, thank you.
Thank you.
Hello. Great talk. Do you have any advice for testing async code? Because in async code, you can't really predict who's going to answer first in which order. So in tests, you usually expect for deterministic stuff, but that doesn't quite happen. So any advice for testing async code?
Yes. Scheduling callbacks, and so first you can have a fixture. If you're using PyTest, there is a fixture that can bring you an event loop kind of wherever you're executing your test. So this is super handy. And as well, you can schedule callbacks. So for example, if you're waiting on a feature and want to make sure that this feature is executed in your test, you can schedule a callback and wait for that. So this is helpful as well. And I'm pretty sure there is some kind of helpers for PyTest and AsyncIO. I think it's PyTest AsyncIO or something like this. And so it's pretty handy, but yeah, otherwise you can often have a hard time making sure that actually if everything is getting executed in the event loop, and this is tricky, and I don't really know any other approaches.
Thank you.
Hi, great talk. So I just have two questions. So first is like, I'm really trying to understand how the awaiting the futures work. So for example, if you schedule a task, like you create a task,
Yes.
and then you have a function call that is not async, does that mean that like my task is already performed in the background, and then after I do the, let's say, call 2 or 3 functions, and then in the end I write await the task, does that means like now I'm awaiting the task to complete, or if it's not yet completed, or like as compared to like other languages, like I had experiences with .NET, the way in .NET it works is like they start the task that you created, and then if it's not yet completed, when it reaches the await, it awaits the program.
Yes.
But in Python, I think I don't, the thing is like the await is kind of misleading sometimes, because it says when you write await, it's actually starts the task or something like that.
Yes.
So can you share some thoughts on that?
So yeah, I think there is as well a lot of differences with like promises. So in JavaScript, for example, the equivalent of future is promises, and they are eager. And so it means that when you create the promise, it will start executing by itself and basically run the first step until the first await. And from the spec, I think you can do the same in Python when you're creating your task. So when you just create the task, it will execute the first step of it until the first await expression. But by default, if you just create a task, if you don't pass it to an event loop and explicitly asks for, like the event loop is not explicitly running, it won't do anything.
So if I pass my task into an event loop and then have some synchronous operation, will that, as due to the GIL lock in Python, will that run in some other thread or background, or first my event loop will work on my async function and then my synchronous function, and until it reaches the code block is, let's say, for example, the 2 or 3 lines is creating the task and adding it to an event loop, and then there is some synchronous function calls, and then last line is the await function.
Okay.
So what will be the call stack here? Like how will it?
So you just call the function without like really getting the future and awaiting them, right?
Yeah, like I just create a future. So I want to do some two tasks in the event loop.
Yes.
Have some synchronous task run after that, and then if my tasks that are supposed to run in the background in the event loop has not yet completed, I will await till it completes and exit the program.
Okay. So I'm not sure the way the flow of what you mentioned. But normally when you will create your task, if you're doing other synchronous stuff, they won't start executing
Right.
until actually they are scheduled. And it depends how you created them. But if they are registered in the event loop, from the moment it will start executing again, they are scheduled to be executed, because as we saw, there is a call soon thing. And basically, when you create your task, it will schedule them with the call soon. So the first step of your asynchronous function will have to run during the next event loop tick. And so when you're actually awaiting, this is when this next tick will happen.
Right.
So you can start schedule the execution of the function, but they won't really start to execute unless you have an await instruction that will actually kind of give back the event loop and start a new tick and a new run once function execution that will pop all the handles that are ready to be executed.
Right. And one last question, like, what's your way to cancel tasks that are scheduled? Like, for example, what happens is like, I have, let's say I have a UVCon server running a FastAPI, and I have a event loop that can schedule some tasks, but I get let's say a OS signal to stop the server in certain cases, like I want to do a update of the server or something. Generally, every time you cancel those tasks, it gets into those task cancelled errors. If you close the event loop, even if you pass the signals internally, it gets into an error. So what's the best way to approach these scenarios? Because if let's say you have a API that creates a lot of background tasks, and then you have to deploy a new update on this, how do you handle those already scheduled tasks that needs to be somehow gracefully stopped in this manner?
So it wasn't in this implementation, but as well features and tasks can be cancelled, which means that instead of being executed when they are in the ready queue, they will just be discarded. And so if you want to avoid that, I think you can shield the promises, which means they won't really be discarded and you will be able to execute some code before that happens. And so I'm not 100% sure, but I think it can help. And as well, if I remember correctly, in FastAPI, for example, I think you have some handlers for those kind of signals. And when we want to gracefully shut down the server and the whole event loop without, because as we saw, there are like the file descriptors, and without like keeping everything still open and in a messy state.
Right. Yeah. Thank you so much.
Thank you.
All right. Let's give Arthur.
Thank you.